Hello. So today for my lesson, I would like to introduce a fundamental theorem in probability called Bayes' theorem, spelled thusly. Now, the theorem is quite old. It came about in the 1700s, and it has to do with conditional probability. So the theorem is thus. The probability of event A happening given event B, knowledge of event B, is equal to the probability of event B happening given event A times the probability of event A over the probability of event B. And what this theorem allows us to do is it allows us to update our prediction on A. So initially we have PA, which we'll call a prior probability. Prior, this term is used a lot, as well as this term. And then we update A as the posterior probability after we get the information from B. So it gives us a way of updating our probability of A happening given that information on B. Now, I want to introduce an application of this theorem in the famous Monty Hall problem. So Monty Hall, and the problem is this. There are three doors, door here, door here, and door here. And behind one of the doors is the car, and behind the other doors are goats, which I'll represent with these horns right here. There's a goat, and there's another goat. Now you want to win the car, and the game works like this. In round one, you pick a door. Then round two begins with goat, a goat being revealed behind some door that you did not choose. But you can only choose one door, so there's two goats, so there's always going to be a door for the goat to be revealed. Um, and then you either stay with your current pick or you swap doors. So let's apply Bayes' theorem to this problem. Let's let A be the event that car is behind the door you chose in the first place. Door chose in one, and B be the event that the host reveals a goat. And the host will not reveal a goat behind the door you chose, right? As stipulated earlier in description of round two. So we write what is the probability, the updated probability, a posterior probability, that the door that we initially chose has the color behind it, given that the host has revealed a goat. While applying Bayes' theorem, it's this. It's the probability that the host has revealed the goat, given that the car is behind the door we chose, times the probability that the car is behind the door we chose in the first place, over the probability that the host reveals a goat. Well, probability the car is behind the door we chose in the first place, there's three doors, so it's just 1/3. And actually, the probability that the host reveals a goat is the same as the probability that the host reveals a goat given that the car is behind door A, which is 1, because as stipulated, the host must always reveal a goat. Therefore, the probability that the car is behind the door we chose after the host has revealed a goat is in fact 1 times 1/3 over 1, which is of course just 1/3. So the probability hasn't changed at all that the door we chose has the car behind it. But we know now have the opportunity in round two to switch after the goat has been revealed, and we know which door has a goat behind it. So the probability that it's not behind the door we chose in the first place, given that the host has revealed the goat, is 2/3. But we know which door not to choose because the host has revealed a goat behind one of the doors that we not have not chosen. So in fact, you want to switch because the probability that the goat is behind the door that you have not chosen is 2/3 because you know, sorry, the car is behind the door you're not chosen is 2/3 because you know one one door that does have a goat behind it. So in fact, you want to switch. Thank you for listening.